Thank you. Hi to everyone. Let me join the previous speakers by thanking the organizers for putting up this workshop and for inviting me here. I checked, and the last time I participated, it was not as nice because it was during COVID period, so it was everything online. So it's much nicer to be here around together with you. So thanks. So what I'm going to tell you today is about a series of papers that make up a program in which we are trying to understand a certain aspect of the string compactification. And the way I'm going to package this today is how we understand gravity decoupling in string compactifications. This bunch of papers and some work in progress done together with some students at IFT Madrid, Alejandro Blanco, a former master's student, Alberto Castellano, a former PhD student, Luca Melotti and Lorenzo Paoloni, which play a prominent role in these papers, current students, Luca about to leave, and Max Wiener, former PhD student, and now a racing star in Hamburg University. So, what I'm trying to talk about today, the motivation is the Swampland program again, which goes into the same context as Gary's talk. Well, this is not going to be a Swampland talk, but is heavily influenced by the Swampland program. Okay, so the Swampland program, which I assume many of you know, but let me quickly go over what it means. What's the idea is trying to really understand all the effective field theories that can be embedded into a theory of quantum gravity that are compatible with a fully fledged quantum gravity theory. The way that people have been trying to do so is by proposing some so-called Swampland criteria, which is a bunch of conjectures that then we try to motivate or test in one way or the other. Most of the tests that people have been doing is by using string theory and in particular string compactifications to get the effective field theory out of it at low energies. So this has been given a bunch of results, a bunch of proposals, a bunch of ideas that are out there in the field. And the result is a growing web of interlinked conjectures, like Gary illustrated with only one of the pillars of the Swampland program, which is the weak gravity conjecture. He says it's not one conjecture, there are many of them. And outside the weak gravity conjecture, there are even more that are also linked to each other. Now, if Gary talk about the weak gravity conjecture, why wouldn't you work? Okay, good. I'm going to use another pillar of the Swampland distance conjecture, of the Swampland program, which is the distance conjecture. Again, this is not a Swampland talk. I'm not going to be proposing any conjecture here today. There was a time in the Swampland program where very quickly you had to propose some conjecture if you have some idea. This time is kind of gone. Nowadays, what people do is they try to learn from all these results, to use the conjectures to get something, well, to put them to use to something different. And that's what I'm going to try to do. I'm going to use many ideas and results of the Swampland program to get a new perspective on gravity decoupling limits. So what does the distance conjecture say? It says, well, if you have an effective field theory, it will have a field space, which in some cases is a model space. First, this thing is not going to be a compact manifold. It has to have some asymptotic limits. You can go to infinity in the sense of distance along this field space. And then when you do, there will be a tower of states, an infinite tower of states that is going to come down exponentially fast in Planck units. So the mass of these states are going to go, in Planck units, is going to go exponentially fast when the distance is also measured in Planck units, okay? And this is going, again, happen to these asymptotic spaces, which we typically identify with the regions of the theory where we have parametric control. Okay, I'm going to be a bit more precise about that in a minute. Now, the conjecture doesn't tell you what is the value of this parameter here, lambda, nor the nature of the tower of states, what they are made of. These are important things that people have been working out to try to specify. In particular, the value of lambda, if it's order 1, it will constrain Transplanckian trajectories, Transplanckian excursions that are important if you want to build some model of large field inflation. So, I mean, even if very theoretical in nature, it has direct impact on the models that we try to build in high energy physics out of string theory. Very good. Okay. So this is the picture that tries to summarize what the distance conjecture is about. Here in Planck units, well, you have an effective field theory. You move in this field direction. You're very happy moving and going somewhere. I don't know why, but you are going there. And then when you go too far in Planck units, then you see this tower of states going down and telling you that if you try to do physics above this scale, which I call M star, which is the typical spacing of the tower, well, you have to change the effective field theory because you have to integrate in all these states and something is going to happen. The simplest example that can happen is that, well, you see a tower of Kaluza-Klein states and then you have to go to a higher dimensional effective field theory, okay, as an example. Now, how can you interpret this picture when it comes down to mean something in terms of the effective field theory that you're trying to work with? Well, I kind of see two interpretations. If you see more, please tell me. One of them is, okay, imagine that I try to do physics at this energy lambda EFT, which is fixed in Planck units. I don't know, 1/10,000 Planck units, okay, Planck mass. I want to do physics here because I want to do physics here. I want this to be the cutoff of my effective field theory. Then when you go along this direction, at some point, you have to cut out your field space. I mean, you cannot use this effective field theory any longer. You have to include this tower physics. You have to change the theory because you have to include these guys, okay? So in this interpretation, you have the distance conjecture, you have this asymptotic limits. You need to have them, but then they are going to be cut down when you try to do physics at this scale lambda EFT in Planck units, which is fixed in Planck units. The second interpretation is, let's not fix what lambda is, but imagine that my effective field theory makes sense all the way as I go in this direction. Then what it means is that this is the maximal value for the cutoff of your effective field theory, which lives with all these guys integrated out. And so it means that necessarily as you go in this direction, the cutoff of your theory in Planck units is going to go to 0, or if you measure the Planck scale in the cutoff of your effective field theory, it's going to go to infinity, which is typically the statement that we make when we decouple gravity. We send the Planck mass to infinity in some units, natural units for the effective field theory. All right? I'm going to focus more on this interpretation because this is what is going to happen for certain string compactifications, and this is where the gravity decoupling story starts. Okay? Good. Besides my interpretation and my things, people have been looking at the distance conjecture for a while. Just like the weak gravity conjecture, the same thing happened. If you look in Spires, there was kind of a dead thing, and all of a sudden, bloop, after Bicep, things become to get a lot of attention. And even if the initial formulation was based on a very simple example, people managed to build very non-trivial tests of the conjecture that gave it a lot and more interest and mileage. So this is perhaps the setup that gave it a lot of evidence to the conjecture when people start looking at effective field theories that come out of string theory, and they have 8 supercharges in 4 dimensions. Okay. Here we have no scalar potential, so we really have a model space. We have gauge and matter field, so we have a lot of interesting stuff. And then we have this simplification that the model space is locally a direct product, so we may focus on one product, the vector multiplet of the hypermultiplet. No? The particular realization of type 2 compactified Calabi-Yau threefolds, very useful because we know a lot of the moduli space of these guys, we know the metric, we can really compute a lot of things. And this knowledge was enhanced, motivated by testing the distance conjecture. Okay, I don't manage, never mind. So, in particular, the first non-trivial test was done by looking at this factor of the moduli space, the vector multiplet moduli space that controls the strength of the gauge interactions. Okay, and it's going to be very crucial in what we're going to talk, because then you can compare the strength of the gauge interactions among themselves and with the gravity. We know the moduli space metric exactly because they are determined by a Kerr potential that in turn is determined by a pre-potential. So we include all the corrections, perturbative, non-perturbative, in this metric. So the most convenient realization of this story for many things is when you compactify type 2 string theory in a Calabi-Yau threefold, then you have this exact Kerr potential that has this form, and you know what the particles that are charged under the gauge interactions are. They are D3 branes wrapping 3 cycles of the Calabi-Yau, and if they are special Lagrangians, then they are BPS particles, and you know what their mass is in Planck units given by the formula. So you can compute a bunch of things. You can see if there is, how the states, what the mass is, and if they really furnish a tower that goes exponentially fast. This is what was done initially by these authors, and they came with a classification of infinite distance limits based on some previous mathematical results, and they interpret that, well, as you approach an infinite distance point, you have a gauge coupling that vanishes, so an exact level symmetry, which is also very bad but set another conjectures, and you have this tower of particles that become massless exponentially fast, just as predicted by the conjecture. So this was a huge thing, and people start taking more and more interest in these kind of setups, similar ones. When towers arise, how do they look like, and what's about them? Recently, this whole thing has been revisited and made more precise by Timo and collaborators. And I don't know, Timo, you're going to talk about this setup in your talk. So more about this in a couple of days. So stay tuned, okay? Now, by using a mirror setup, there was a refinement of this story, which is very convenient when you want to trade the big picture of what's going on in these limits. There was this proposal by Sunjun, Timo, and Wolfgang, saying that, okay, not only you have this tower that goes down, but the nature of the tower is very constrained. You have essentially 2 options. Either it's a Kaluza-Klein-like tower, so you go to a decompactification limit when you go along this direction, or it's a tensionless critical string, so you go to like a weak coupling limit that we are used to in string theory. Okay, this is what's packaged into emergent string conjecture, essentially saying that for the leading tower, the one that tells you how you have to change the effective field theory when you go above this cutoff M star scale, there are 2 options: higher dimensions, or you start seeing string theory. Okay, very good. Now, this distance conjecture story is also linked with the weak gravity conjecture story that Gary was telling us about. And how is it linked? I'm telling you this because it is going to play a role in what I'm going to talk about next. They are connected, very nicely connected through BPS extremal objects, not always, but in supersymmetric effective field theory, this is usually the case. Okay, in the case of 4-dimensional n equals 2 theories, the tower is made of extremal BPS particles, and along the limit you have that the mass goes to 0 as predicted by the conjecture. The charge, the physical charge, not the central charge, but the physical charge goes to 0 as well, but the charge to mass ratio states of order 1. And the underlying reason is that if you try to do a black hole solution with these extremal objects, well, I mean, this is what is going to be the extremality factor, but as well is linked to this parameter of the distance conjecture. So this essentially gives you a rationale why this parameter lambda is order 1, and you do it through the black hole solution of these extremal objects, okay, as pointed out in these papers. So the main message that I want to say is that you can really learn a lot about this conjecture, about the abstract form, by looking at physical objects like black holes made up of the particles that are in the tower. You also have a connection of this sort if you look at strings, other BPS objects, which are strings whose back reaction, when you look at them, they realize the infinite distance limit. For instance, this in 4 dimensions is so-called EFT strings, which are a very particular kind of axionic strings, or in 5 dimensions, they supergravity strings. They are special objects. They're purely gravitational, which is one of the lessons that we learned from the Swanland, that there are some objects there, physical objects, that are purely gravitational, because if you decouple gravity, they disappear. And then the consistency of the worldsheet theory tells you a lot about the bulk theory. Okay, if you want things to work fine in the worldsheet, then you're going to have to put some constraints on the couplings in the bulk theory, in the bulk Sugar theory, that can even constrain it almost completely, as was like pointed out in this different setup, 6D, 4D, and 5D by these authors here. And I think probably we learn more about the subject on Friday. All right. So this is just the motivation part of the talk. Let me go over the main points that I wanted to emphasize, that I'm going to borrow from the Swanland program to say something new. Okay. So the first insight is that many statements of the Swanland program that may look like pull out of the hat from the beginning can make more sense if you realize them through physical objects. This may look like something completely tautological, but this is how things evolve naturally. There are certain objects that are of gravitational nature, not all of them, but some of them, like these supergravity strings, that contain a lot of information related to this Swanland program and how quantum gravity talks to effective field theories. In supersymmetric effective field theories, there are typically BPS extremal objects, and the back reaction, the physical, how the back react on the effective field theory probes asymptotic regimes in field space. And that's why they are related to distance conjecture. There's a mathematics of how these charges are arranged and what they do and what information of the model space it contains. I not particularly want to go into that. But what I want to say is that what if we look at the objects that are not these guys? Are these completely disposable? Are they highly uninteresting, or can we learn something from them? So we have the gravitational objects, which are BPS and extremal, for instance, particles, strings, and so on. But we have other objects that could give us extra information. For instance, we can have BPS particles in a 4D n=2 compactification that are not extremal. What do I learn from this guy by looking at their properties and in relation with the distance conjecture? Well, the point that I will try to make in the following is that you can learn a lot, and you can learn about, for instance, in particular, about the physics of gravity decoupling limits. Okay? So far, so good. These gravity decoupling limits, I'm going to call for short rigid limits. And the name comes from, well, from what we know in again, 4-dimensional n=2 effective field theories. Here is very well understood from a mathematical viewpoint what's a gravitational or supergravity system versus a non-gravitational system. We have different geometries in moduli space that describe one or the other. No? So let's this be the supergravity action in 4 dimensions for the vector multiplet. This is specified by all these quantities here, the metric, the kinetic terms, gauge kinetic terms, the theta angles, they are specified by a prepotential. That's old story, almost 30 years ago, old. And then with a prepotential, you can either talk about supergravity effective field theory or a supersymmetric theory without gravity. The difference is, for instance, in the Carré potential, you have this famous log in here, while here you don't have it. And this implies that the moduli space metric looks like this in the supergravity case, and like this in the rigid supersymmetry case, as well as the gauge coupling constant look like this, and this thing is way more horrible to write down. Now, already from these expressions, you can guess how to go from a supergravity description to a non-supergravity description to a rigid description. You need to recover this piece on the metric. So what you can propose is just that this piece of the metric, of the supergravity metric, is negligible compared to this one. Okay, so this relation. If you interpret this factor in here as a change of the scales, like you no longer are going to have the Planck mass as your cutoff scale, natural cutoff scale in a rigid theory, but you're going to have something else, then you precisely recover this metric. Okay? So this is a very silly way of connecting supergravity to non-supergravity n equals 2 four-dimensional theories by asking that along some limit, this happens. Is that okay? All right. Now, this is very pretty, but now I want to do what I promised, which is interpret this in terms of physical objects. Okay? So what are the physical objects in here? Well, for the n equals 2 vector multiply, there are BPS particles, which are charged. These are the quantized charge. They have the magnetic and the electric. They have the mass that is controlled by the central charge if they are BPS. And we have these nice formulas. And they have a physical charge. Okay? With this Q tilde here, it means that, well, it takes into account the Witten effect here. So one of the identities of special geometry, which is the geometry that controls the moduli space of supergravity for the n equals 2 effective theories, tell us that this is true. If I compute the charge to mass ratio of these particles, I have this identity. All right? And the interpretation is a no force condition between BPS particles. So essentially, this is the gravity attraction in gravity units, so normalized to 1. This is a charge repulsion in the same units, normalized to the attraction of gravity. And this is the exchange of moduli, which are massless. So they will also generate an attraction. When you put this equality together, you can interpret them as the repulsion between two BPS particles equals to the attraction, which is the no-force condition that we all know and love. All right? Now, from here, you can see that a rigid interaction is precisely when this charge-to-mass ratio blows up. It's super big, because then this one here is completely negligible, and the no-force condition comes from a cancellation between the charge repulsion and the moduli attraction. Gravity doesn't play a role in the no-force condition, which is what should happen for a theory without gravity, okay? Supersymmetric theory without gravity. Now, one can check that this is precisely the previous condition that I was telling you about, that this piece of the supergravity metric is much smaller than this one for a certain kind of particles, for a certain kind of charges that are interpreted as monopoles. And one could draw the same thing for BPS strings in axionic regions. So what I'm trying to say is that one can detect when a certain sector of your compactification approaches a rigid limit by looking at these quantities. I just compute this. It's order 1, gravity is there, in equal footing as the rest. It's much bigger than 1, then gravity is not the weak gravity conjecture, it's the super weak gravity conjecture. It's really weak, and it becomes negligible for these particles. Particles, they don't care about gravity, okay? So, okay, so this observation led to a kind of new picture on rigid limits, which is what I will try to exploit during this talk, in which you can define, well, not only an infinite distance limit, it could be finite distance too, by the way, but a particular kind of limit or trajectories where something happens that tells you that a subsector sum gauge interactions work in a rigid way. They are much stronger than gravity. They don't care about gravity. Particles charged under them, they communicate as in a theory without gravity. So imagine that you take a trajectory in vector multiplet moduli space, which is the setup that we are looking at, in which some charge to mass ratios stay order 1, like the ones of the distance tower. This is what we will call the gravitational sector of the theory. There are a bunch of gauge interactions that stay gravitational. They are as important as gravity all along the way, all along this limit. But then some of them, the charge to mass ratio become infinite, which means that the exchange of particles of gravitons is completely negligible, and we are in a rigid theory. So the idea is that along these limits, you can separate your space of U1s into two: the ones that are gravitational, equal floating as gravity, and the ones that don't see gravity anymore. Okay. Now this is easier said than done because, okay, this is a lattice of particles, many things can happen. But when the gauge coupling of the rigid, what we call rigid sector, is much larger than everybody else, then this set of charges, quantized charges whose ratio goes to infinity, forms a sublattice, and it's very easy to identify what is the set of U1s that are part of a rigid theory. Okay, so I can say, okay, look, this 1, 2, 3 U1s are part of a rigid theory, all the rest are part of the gravitational sector. And then I can ask the question, do these two sectors decouple from each other? Okay, before that, it's hard to say. This is important because this story is not only going to be about gravity and U1s. It's going to be a bunch of U1s that include the graviphoton and another bunch of U1s that decouple from all these guys. Okay, so in practice, how do we get this charge to mass ratio to go to infinity? There are two possibilities that then you can, of course, combine. You can either take the charge to infinity and the mass stay constant. This will be a strong coupling singularity, okay? Jerez Douglas, I don't know. You go to some strong coupling singularity that is supposed to be in the interior of moduli space. Or you can take the charge more or less constant because, well, you want the gauge couplings to not to go to zero coupling and become non-dynamical. And then you take the masses in Planck units to 0, okay? Two ways. Now, this can happen is at infinite distance singularities or a finite distance singularities like the conifold. Here, we're going to focus on the infinite distance, although one could extend what I'm going to say to the distance singularity in some way. But because of the sake of the distance conjecture, this is what we're going to have in mind. We're going to look at limits where the masses of certain particles are going to go to 0 in Planck units, but their charge, the physical charge, how they couple to the U1s, the gauge coupling of these U1s are going to stay constant. All right. So this is essentially the general picture that you get when you look at many examples. There is a natural choice for the cutoff of the rigid theory, which is the M star of the distance conjecture, which is there because we are, if we live in the distance conjecture, which we should. And this is how the charge to mass ratio looked like: a constant, this quotient that goes to infinity, and then this charge to mass ratio of the rigid theory defined in this way, essentially with respect to the natural cutoff. Now, to have dynamical degrees of freedom below M star, we don't want these couplings to go to 0 very fast. And so to have a thing that blows up, we need the charge of the objects, charge under the rigid effective field theory, to be around this scale. okay? Because otherwise this will not blow up. So you can have two options, or at least in what I've seen these two different options. You can have a tower that is above M star, never below, because then you will just have something below this guy, or some particles that is close to below to M star. Both in these ways, if these are BPS particles, you generate this picture in which the charge to mass ratio blows up. Now, this for this to work, which is pure IR information, you don't need to have an actual BPS particle in here. You just need to have a charge whose would be BPS charge and mass behaves in this way. But when you do have particles, which happens in several instances, when you do have BPS particles in here, which is an ultraviolet information, particularly in this case, then integrating these guys out generate a non-trivial rigid field theory in the deep IR, which has non-trivial interactions whose couplings run, has a non-trivial curvature, and can be detected via divergence in the moduli space curvature, okay? The one in the supergravity one. So there is two ways to detect that you're going to have a rigid limit. One, look at these guys, or another one, more efficient, is to look at the moduli space curvature of the supergravity theory that is going to blow up. This is actually how this whole program started. Let me very quickly tell you how this looks like. Thanks to Strominger, we have this nice formula for how the scalar curvature of the moduli space in the Scala-Villard compactification looks like. You have this constant negative piece and this moduli-dependent positive piece. And the idea is that along certain limits, this thing blows up, okay? When it does, it's because some of the terms of this sum dominates over the rest. And if you look at this, has precisely the form of a rigid curvature, no? That looks like this. So you have a structure, when you rearrange things, you have a structure for the divergent piece of the curvature that looks like this is a quotient that appears in the distance conjecture. This thing goes to infinity. And then you have something that looks like this, which is a rigid curvature. Now, if this doesn't go to zero very far, you will have a divergence. In fact, the two ways that you could think of having a divergence, and then you can take combinations, is that either this blows up and this stays constant, which is what happens in conical-like singularities, or that this blows up and this stays more or less constant, which is what happens in infinite distance singularities. Okay? Moreover, something that we observe is that in all cases, the curvature divergence is bounded from above by the charge to mass ratio of some BPS particle, the one that goes fastest to infinity, which means that for a divergence to occur, some gamma should blow up. And moreover, when this happens, this rigid field theory corresponds, this rigid curvature corresponds to the curvature of the rigid field theory that you detected through the blowing up gammas. So to sum up, everything matches, and eventually this led us to propose a curvature criterion, which tells us, even beyond the setup, that when you have a moduli space curvature that goes to infinity, is because you have some sector of your effective field theory that is becoming rigid, where gravity is no longer important, where gravity is being decoupled from. Okay. So let me do a second recap. So, yeah, from 30 years back, people have been looking at four-dimensional n=2 theories and distinguishing what it makes them to be a supergravity theory or a rigid theory without gravity. That's why this is a very nice framework to describe gravity decoupling limit, because the math is already there. Now what we try to do is to formulate this same thing, but in terms of physical objects, by looking at the charge to mass ratio. When you do that, you say, out of the spectrum of particles, some of them have a charge to mass ratio that go to infinity, and some of them have a charge to mass ratio that goes to order 1. From there, I can look at the U1s under which this guy has charge and divide my space of U1s into gravitational U1s that go together with gravity, that they are married to gravity, and the ones that are not married to gravity, that decouple from them along this particular limit. And these are the second ones are the ones that describe the rigid sector. And then in specific cases, in many cases actually, you can detect the presence of the second guy by looking at the moduli space curvature, which diverges along the limit. Okay? Any questions? All right. Yeah. Yes. Huh? No, no, because you could have a rigid limit where the rigid curvature is 0, and when you plug it in here, it doesn't give you a divergence. Okay. So, but these are very silly rigid field theories, but they can be. Any other questions? Okay. So, before I proceed, there is a disclaimer that I should put out there, to be honest with you. I mean, these features, they are very nice. They are very simple to state. But I mean, if you are really purist, you say, okay, these are potential rigid field theory sectors. But from this algebra, nothing guarantees that there is an actual decoupling of gravity. So to decouple one sector of the vector multiplet from the other, I mean, I should be able to integrate, solve the equation of motions, and the sector number 2 should not influence sector number 1, no? So if I solve for the gravitational sector, which is the one that I want to decouple, integrate out, and so on, the rigid sector should not be entering their equation of motion, or their role should be completely negligible. For instance, I should not have any kinetic mixing between the rigid sector and the gravitational sector. Otherwise, they are not decoupled. Now, how do we do this in practice? The standard mechanism is to say that the rigid sector has a gauge couplings that are much larger or non-trivial, while the other sectors are going to weak coupling. And so when we canonically normalize the fields, all these mixed interactions will go away. And I can integrate them like a free field, for instance, the gravitational sector. Now, the question is this a standard mechanism what is going on? Or are there some surprise in the pocket? Okay. So that's what I'm going to discuss in the last part, because everything that I've told you is kind of abstract, but now I'm going to get my hands a little bit dirty, look at particular setups, look at particular limits, and get some particular and specific behavior for gravitational rigid sectors and so on. Well, let me ask you first, so who in here has worked on gravity decoupling limits? You had to decouple gravity for one reason or the other. Like, you take a limit and you say, okay, I decouple gravity. Come on. I mean, it's not something to be ashamed of. What? Say it again? Oh, so somebody already did it for you, no? Okay, well, no. But okay. What I'm gonna have in mind is a particular kind of gravity decoupling, which is the one that you get when you look at the string compactification, which is the framework that I was looking at. In here, there are several ideas of how to get a theory without gravity. Some of them have been super popular, like this large extra dimension theory. And they come in all different kinds of shapes and forms, but they all have the same ingredient. At least these the ones in here. They could be other options, of course. But one of the most popular ones, they have the same ingredient, which is localization. You have a compactification, you have extra dimensions, and you have gravity that propagates in all the dimensions, but some gauge interactions are localized. You can localize them because of the geometry, like originally in here, You can localize it because you have a D-branes where that fill out some slice of the internal dimensions, or you can localize it again because of a combination of both, like in this F-theory setup. The idea is that when you localize in a lower dimensional slice of the extra dimensions, this interaction is much more intense than if it's diluted all over the place. At least if the dimension of the bulk, the size of the bulk, is much larger than the size of the slice that you are talking about. Okay, this is what people also have been used for model building, like this F-theory and D-brane story illustrates very well. Okay, so and you can check everything about it in this fantastic review by Gary and collaborators. All right. Okay, so, but in this setup that I'm talking about, I'm going to go for one of these options, which is the geometric engineering one, which is you localize certain gauge interactions due to the geometry of the internal space. And you see, for a string theorist, if you are a string theorist, this is enough. You say, oh, very well. I mean, look, the gauge interactions, they are here, very localized, and the gravity is all over the place. It's diluted. The interaction is diluted. I'm decoupling gravity. I can even take the Calabi-Yau to be non-compact. So decoupling gravity, which is very nice. But then if you're an effective field theorist, how would you tell the effective field theorist what's going on? How would you, I mean, you cannot talk about extra dimensions. The effective field theory is below the Kaluza-Klein scale, doesn't know about the extra dimension, doesn't know about the branes, it just has a Lagrangian. So how would you explain in terms of the 4D Lagrangian what's going on? And the standard answer is MP goes to infinity, which is very nice, but it may not be enough. As I told you, as I tried to communicate to you in this sort of compactifications, the gravity comes together with a bunch of U1s. And you should decouple all these guys from the rigid field theory. So it's not only gravity, but also some U1s that come together with it that should be decoupled. Okay? Okay, so what I'm going to discuss last is how this happens, or some ways that we have found how it happens from the viewpoint of an effective field theorist. First, let me point out that the classes of for the n equals to rigid field theory that one obtains by taking limits, well, there are many, but the most famous one like Cyber-Witten theories, super famous. And then higher dimensional rigid theories, well-known rigid theories like superconformal field theories or little string theories that you dimensional reduce to get a 4-dimensional field theory. Okay? Okay. So as I promised, I'm going to get my hands a bit dirty by going to a specific setup, which is a compactification of type 2 string theory in a Calabi-Yau. First, I'm going to look at large volume limits, but I'm going to stay in this vector multiplet, which means, sorry, I'm going to stay in vector multiplet of type 2A, which means playing with the Keller moduli of the Calabi-Yau. And in particular, I'm going to take one of the Keller modules and send it to infinity and go 2 cycle is going to grow, or 4 cycle is going to grow very, very large. When I do that, I have a description of the prepotential that looks like this. And then I have a bunch of infinite distance limits that are where the distance conjecture is going to be realized, and everything that I was telling you before is going to be realized. Okay? All right. Particularly simple is when I take like one limit in which I grow one Keller modulus and all the rest are frozen. This is called EFT string limits, and they have a bunch of features that, okay, they simplify the story, so that's what I'm going to tell about today. So let me consider these limits. I'm in a Calabi-Yau. I have a bunch of sizes of 2 cycles. I take one of them to go super large, maybe together with other guys, in this particular way. Because I want to stay in the vector multiplet moduli space, I need to go to strong coupling in the 10-dimensional coupling. And the volume grows like this with this power, where this W is an integer that can be 1, 2, and 3. So luckily for us, people has classified how the different infinite distance limits look like and what's the physics associated to them for this family of limits, which is a lot of them, okay, for any Calabi-Yau. So essentially, there are three options. When the volume grows like a cubically in this variable, we have a compactification to one extra dimension. And what we see is above the distance conjecture scale is M-theory compactifying the same Calabi-Yau. When this other option happens, in terms of, I mean, this is a bunch of constants and vectors that you build from the direction which you grow and the triple intersection number of the Calabi-Yau. I haven't said these are triple intersection numbers. So these are topological quantities that you can easily compute. When this happens, you have a volume that grows quadratically, the compactification 2 dimensions, you get F-theory in the Calabi-Yau, and when the volume grows linearly for this kind of limits, you have an emergence free limit and you have an heterotic dual. Okay, so three options, and then I can look at them one by one to tell you how you can have a rigid field theory in each of them and how it decouples from gravity and their friends. To get some more intuition, what one can always do is to look at these limits from the viewpoint of M-theory. Remember that we go to strong coupling, so the M-theory description is very natural, right? In M-theory variables, what we have is not just the Calabi-Yau. What we have in Calabi-Yau, we have M-theory on the Calabi-Yau times a circle. The SW3 limits are finite distance trajectories, and the other two are infinite distance in M-theory metric. And what happens is when I grow this guy in size, this guy doesn't grow in size, but the radius of the compactification radius of the circle does. Okay. When, moreover, when this matrix is singular, when it has a non-trivial kernel, then in this picture I have a device or a force cycle that stays of constant volume, even if I grow the size of my extra dimensions. There is some slice that some four-dimensional slice that stays of constant volume, while in M-theory, this four-dimensional slice shrinks to 0 size. So you see here, this is how localization is implemented in this setup. In M-theory, when I go an infinite distance limit or finite distance limit, I shrink some force cycle to a point, and the gauge interactions associated to these force cycles are localized in a point or in a submanifold. Okay, so this is localization, but this is not how effective field theorists would look at this and say, okay, I don't know what you're talking about. Please tell me what the hell is going on. Now, from the effective field theory, we have this picture, remember, no? And then the tower and so on, or whatever. In this particular case, we have a tower of states that are charged under the rigid field theory. And then we have that the fields that remain dynamical below this distance conjecture scale, below the tower scales, are the ones that are related precisely to the kernel of this matrix, that we need to be non-trivial in order to have a rigid theory. The prepotential is a truncation of the previous prepotential to these variables. So this it tells you precisely what is your rigid field theory, which you want are part of your rigid theory, which is a small subsector of the whole thing. You can compute the rigid curvature, and then everything works out as expected. You have a curvature divergence because this thing stays more or less constant, and this thing blows up. Okay? What I'm trying to say is that in this large volume case, it's very easy to identify what the rigid field theory is, and everything works as previously explained from a more general viewpoint. Now, how do you decouple gravity? Because, I mean, I'm talking for hours, but I'm not telling you how we decouple gravity, no? And let me take the double equal free limits. Remember, it's a decompactification to one more dimension, to M-theory on the Calabi-Yau times the circle. Here, the rigid field theory is the daughter of a 5-dimensional superconformal field theory that you dimensional reduce on a circle. Okay? This thing is localized on a device or force cycle shrunk to a point, as Witten taught us. And from there, you can get a rigid field theory when you compactify this extra dimension. Now, how does if you are here, if you don't know about all this, you are a humble effective field theorist that lives here at zero energy, what do you see? You see this gauge kinetic matrix, where these are the different vector multiplet sectors. So this column is the U1 that corresponds to the 5-dimensional Kaluza line. This column is the U1 that corresponds to the direction of the limit, the field that you switch on to go along this infinite distance. This last column is the rigid field theory, the kernel, and this is everybody else. And this is 1 over g squared, which means that this goes to zero coupling, zero coupling, zero coupling, and this is constant. All right? And these are the gammas. This is order 1. This is divergent, but less divergent than this one that is the one from the rigid field theory. So here you get a pattern of how gravity decouples. This guy is very simple. This guy has the largest gauge couplings of all of them. So when you canonically normalize, you will be able to integrate at all these U1s from the one of the rigid field theory. This is textbook decoupling in field theory, in gravity. So this is actually quite simple. You see that this guy also have a diverging gamma. This guy, this you could call a rigid field theory sector, but you could not decouple from this one because the gauge couplings are similar. So it's only this guy that you can really decouple from all the rest, and in particular from all the gravitational sector, which are these two guys, the direction of the limit and the U1 of the tower. Is this okay to you, or boring, or nothing? Okay. Yes.
Could you mention what's the rest? This third one?
These are a bunch of non-effective divisors whose volume goes also to zero size, but they are not. It's not really the shrinkable divisor. Okay. Or if you want, in terms of the type 2A, yeah, let me say that. So these are divisors whose volume grows, but not as fast as the direction of the limit. So it's a bleeding, and so in M theory, I think it will be shrinking. Okay. So if you would wrap brain in there, the mass will go to 0 in Planck unit. You don't wrap anything, but if you did. All right. I mean, geometrically, these are guys that are not on the kernel and are not in the direction of the limit. So good. Let me go to guy number 2. Oh, I'm running out of time. Which is double equals 2 limit. Remember, these are the compactification 2 dimensions to a 6-dimensional superconformal field theory. Here we have a more complicated frame. We have more guys in the game. We have the 5-dimensional Kaluza-Klein direction, the 6-dimensional Kaluza-Klein U1. We have the direction of the limit. We have the kernel, and then the rest. I mean, what is the rigid field theory? It really depends which kind of divisor is in here. So there is a variety of possibilities geometrically, but in terms of effective field theory, you get this universal pattern. Now, here you have 3 guys that are gravitational. Okay, I mean, the towers and the direction of the limit, they're always gravitational. This is what we learned from previous things. These guys are not. They don't have to be. Now, these 3 guys goes to weak coupling, which means that I can easily decouple it from a rigid field theory, but not this one. This one is a gravitational U1, it's the direction of the limit, and the strength of the gauge coupling stays constant when I proceed along this direction. So there is no parametric difference in gauge couplings. This is not parametrically weaker, the gauge coupling, than this one. A priori, the field theory notion of how you decouple by hierarchy of gauge couplings does not apply. So you did field theory, say, well, okay, yeah, maybe I can tune it, but it's not something that comes naturally. Why this sector decouples from this one? Okay. What is true is that this guy has the largest divergent thing, blah, blah, blah. Last one is even worse. Here, there's going to be a heterotic dual in which the rigid field theory, when you do type 2A heterotic duality, is going to be housed by a NS5 brane in the heterotic dual. So here, you have, again, 3 sectors that are gravitational because the charge-to-mass ratio stays of order 1. There's a 5-dimensional Kaluza-Klein, the direction of the limit, and all the other Kaluza-Klein sectors, you could call it that way. And then you have the rigid field theory sector. Here, the direction of the limit goes to strong coupling, at least when you express things geometrically. So there's really no way in which you can apply the usual field theory notion of this guy decoupling from this one, because it's the opposite of what you would like to. Okay? So here there's some drama involved, in the sense that you have a gravitational U1 that goes to strong coupling along the limit. So this guy, I mean, is strong compared to these two, but is not the strongest one. Okay. Okay. So to sum up, for this kind of limits, the rigid field theory, you see this rigid metric is very nice algebraically, but it does not contain the gauge couplings that are strongest, at least not in this frame which I'm describing things. We have some gravitational U1, the direction of the limit, that is either comparable or parametrically larger than the couplings on the rigid field theory. And this is a huge turn down, because, I mean, why am I talking about gravity decoupling? From the viewpoint of a string theory, you say, okay, I'm happy because I know there's localization. It should be that everybody else, I can wash it away. But from an effective field theorist, it's a bit tricky. Now, what happens is that the definition of this kernel tells you that all the possible mixed terms between the rigid field theory sector, precisely the rigid field theory sector, and this strongly coupled guy, they vanish. This is the prepotential. You can check it from this point of view. The definition of kernel tells you that you have this cubic coupling for the strongly coupled guy, and this cubic coupling for the rigid field theory, but no mixing between them. And also no mixing at the quadratic level. The only mixing that can happen is when you take into account these exponential corrections. But these exponential corrections, they go to 0 super fast. So even when you normalize the strongly coupled guy, and you get an enhancement instead of a suppression for the gauge couplings, what happens is that gauge couplings, they are super small anyway. They are small exponentially fast, and even this enhancement loses over this exponential suppression. So the string theory intuition works. Localization does the job of the decoupling, but from the effective field theory guy is a very non-trivial thing. You suppresses the couplings that if they were there, they will forbid the decoupling. Okay, you like kill them in terms of coupling, not in terms of normalization of fields. And one can see the same thing for M-theory compactifying a Calavillard. I give you a 5-dimensional theory. Okay, I'm a bit late. So let me go to the last part, which is the Seiberg-Witten limits. Here something similar happens. Well, this engineering from the technical viewpoint, what happens in the Seiberg-Witten limits is there are some so-called the metric essential instantons that tells you that there are some exponential terms, like these exponential terms that I was putting here in the prepotential, that are necessary to have a non-singular metric. Okay, this is the picture of Seiberg-Witten. Here you have this particle which is W boson that is below the Tower scale. And what happens for the prepotential, you have again a polynomial part and an instantonic part, but unlike in large volume, you need this part to have a non-singular metric, a well-defined metric without any zeros. This feature tells you that you have some particles whose BPS mass is exponentially suppressed, while their physical charge is unsuppressed. So this thing, when you compute the ratio, is going to give you very large charge to mass ratio, which indicates that you have a rigid field theory sector. The rigid field theory sector is precisely the U1s under which these particles with exponentially suppressed BPS mass are charged. Okay? And this is where the Seiberg-Witten prepotential come from the same periods and so on. You have the same story that I was telling you about. Is more involved, is more difficult to classify than the large volume limits, but the same physics holds. You have a curvature divergence for them. Now, this is very nice, blah, 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 but how do the Seiberg-Witten sector decouple from the other U1s? In particular, here, I have this particular engineering of Seiberg-Witten, in which you have two vector multiplets and the graviphoton. The gauge coupling matrix is a 3×3. Again, here you have these two guys which are gravitational, and this guy which is the rigid field theory entry. You see, the gauge coupling of these guys goes to infinity, just like it happened for the large volume double=1 limits. And again, you have a similar mechanism because of the features of metric essential instantons that, well, I don't have time to describe because I run out of time. The couplings that would mix these two sectors, they are exponentially suppressed. So even if the normalization of fields enhances and you don't want this to happen, the couplings are so small and they go to zero so fast along typical limits that the decoupling occurs. All right. Let me conclude because, again, as I said, run out of time. So, what we have learned over the years is that the Swampland criteria, the Swampland program, has been very useful to understand the physics of asymptotic limits from a new light. And what I try to do here is to use all those lessons to apply to a particular kind of limits, which is the ones in which some sector decouples from, or gravity decouples from some sector that it becomes rigid. The first point that we made is that one can detect this in a simple algebraic way by looking at the charge to mass ratio of BPS particles or by looking at the model space scalar curvature. From the viewpoint of string theories, that the coupling occurs, it's like very easy to see just by looking at the extra dimensions. I see that you have some localization of gauge degrees of freedom as opposed to the one on gravity. But from an effective field theories, there are some surprises in the box. There are some cases in which you decouple the rigid field theory because the gauge couplings are the strongest, so you can use the usual mechanism. But some others is that the couplings mixing the rigid field theory with gravitational one are tuned and are exponentially suppressed so that the coupling occurs. So that will be all. Thank you. Sorry for.
Thanks for the nice talk. Are there any further questions in the audience? In fact, I have one confusion. When you were jumping from the diverging gamma to diverging moduli space curvature,
yes.
Even before you gave the explicit expression for the n=2 theories, I didn't get the link, in fact, there.
Okay,
Could you perhaps briefly repeat?
It's, yeah. This or not?
Just you gave a qualitative argument before this, right? Maybe slightly before, even before you go to the n=2 specific special geometry setup.
Okay.
How were you motivating the connection?
Yes. Okay, sorry.
What was the general sort of intuition behind the connection between the two of you?
Wait. We can. Oh, it's longer this way. No, I was motivating the link in the following way. In this way, you can have gammas that diverge. But this is something that you can test from the deep IR thing. I mean, gamma, you just take these periods and you interpret them as masses of BPS particles, and you compute the charge, and then you compute the gamma, and you see if it diverges or not. Now, what you don't know, if this Q, the charge, the quantized charge, hosts an actual BPS particle or not. Some Qs are populated by BPS particles. Some others are not. Okay. To compute this quantity, you don't need to know that. And it's enough to know that this goes to infinity to look for a rigid sector. That's it. Now, if this is populated by an actual particle, what you expect that what's going on in here is that the rigid field theory is non-trivial, because to get here you have to integrate all these guys that are charged under them, or maybe this isolated guy, and below this energy you're going to have some couplings and run, like in the conifold. Okay? So when these guys actually exist, you expect a rigid field theory with a non-trivial curvature, with a non-trivial interactions, with running gauge couplings, with gauge kinetic functions that depend on the fields, not a flat metric, but a non-flat metric. That's the expectation. I mean, I don't have a proof, but I mean, like the examples back it up. And when you have this non-trivial rigid field theory in terms of metric, in terms of gauge couplings, in terms of running and so on, then you will have a non-trivial curvature that then becomes a piece of the modular space gravity, the supergravity curvature via these relations. So this is going to be non-trivial, and so this is going to appear as a piece of this sum, and it's going to diverge because asymptotically it's going to look like this. That was the connection. But it's a bit hand wavy. I mean, in examples it works. But
okay, yeah, thanks. If there are no more questions,
Could you say a few more words about the role of the exponential terms in the prepotential? So,
in which case?
On the second to last slide, also for the decoupling.
In Cyber-Witten?
Yes, in the Cyber-Witten.
Yeah. So what happens? Yeah. I mean, this is. I don't have the full picture here because each Cyber-Witten story is a bit. I mean, I cannot look at all these cases in one go like I do with large volume, because they all have their specifics, and we didn't manage to get the big picture for all of them. But what it happens, examples, is that the prepotential, which I haven't shown, it has the piece that is the leading piece. Okay, maybe I can do it with this. Has the leading piece, and then this one. This one contains the coupling between the gravitational U1 and the Cyber-Witten sector, but they are suppressed. Okay, they have an exponential of minus t, where t is the infinite distance direction. So, or they don't have it, and then there's no coupling. So, like all the things that could give you mixing, they're going to go to zero super fast when you go along the direction, even if this direction has a gauge coupling that is very strong. So it works in a similar way to the others, although I don't have a general proof. This is based on examples.
I don't see any further questions. Then let's thank Fernando again for the nice talk.